Hi, today we're going to talk about compound inequalities. A compound inequality is an equality that's joined by the words and or. So it's basically taking two inequalities and putting them into one problem. A type of an example where we have an and situation can be written with the word and, or it doesn't have to have the word and written in it. When you graph a compound inequality that is an and, you will only graph the overlapping region. An or situation has to have the word or between it, and there's only one way to write the solution. And usually when you graph, but not always, the graphs tend to go in opposite directions. Let's take a look at a couple of examples. But before we do, let's just take a look at a solution of a compound inequality joined by and is any number that makes both inequalities true. The graph in an and problem would look like this. It usually has your numbers on a number line. It will have a point colored in, or it could have open circles, but the shading is in the middle. The shading is the overlapping region of the two separate graphs. The overlapping region, those are the numbers that make both inequalities true. A solution of a compound inequality joined by the word or is any number that makes either inequality true. And a solution to this could look like, let me throw in some tick marks there, usually graphs that are going in opposite directions. They can have open or closed circles just like regular inequalities, but then they can go in opposite directions. If I want to graph this first inequality, this is an and situation because it's written as a one inequality has two of them in there, so it's a compound inequality. This is saying that negative 8 is less than x, which is less than or equal to 10. This is the same thing as saying that x is greater than negative 8 and x is less than or equal to negative 10. So let me take this part right here. X is greater than negative 8. So at negative 8 we have an open circle because there's not an equal to sign. All the values of x that are greater than I would shade to the right. Now x is less than or equal to 10. I would go to 10, I do a closed circle, and I shade to the left. But then I'd have to stop at this point and I'd only shade those values in the middle. The values in between these 2 points, and including number 10, are the only values that satisfy that inequality. Number 2, if I have x is less than or equal to 0, so a closed circle at 0, and then I shade to the left. Now, these compound inequalities is just having two inequalities on one graph. X is greater than 9. Color that in. Here are some word expressions that we're going to rewrite as an inequality and then graph them. Okay, this says all real numbers that are less than 1 but greater than 5. Let's think about what that might look like. Okay, filled in some numbers. All real numbers that are less than 1. All numbers less than 1 would look like an x is less than 1. So I would graph that in, but greater than 5. Is there a number that can be less than 1, but then greater than 5? Think of that as an and situation. We said earlier that an and situation has to be where the two overlap. This graph does not have an overlapping region. So all real numbers that are less than 1 but greater than 5, there aren't any for us to be able to do. So we could do like a circle with a line through it, and that would represent the empty set, that there aren't any numbers that represent that situation. There aren't any numbers less than 1 but also greater than 5. Let's take a look at the second example. The grade earned is earned, whoops, that's supposed to be is a B. The grade earned as a B is between 83% and 86%, if I can read that right. So between 83% and 86% is where our grade has to fall, and if it says between, it does not include those numbers. So I'd have an open circle at 83, open circle at 86, and then I would shade in the middle. Number 5, all real numbers that are less than -3 or greater than 6. All real numbers x are less than -3 or all real numbers that are greater than 6. Now remember, in an OR situation, whatever they happen to be, when you put them on a graph, open circle at -3, shade to the left, in OR situation, they do not have to overlap. They usually go in opposite directions. Open circle on 6 and shade in this direction. It doesn't mean that they always will, it's just most of the time they usually go in opposite directions when it's an OR. And should always be shaded in the middle. It's what they have in common. This last example, discounted tickets are available to children under 7 years old. So if I do tickets as my, say, T. So children under 7, so T less than 7, or to adults 65 and older. Tickets greater than or equal to 65. Now since I had such a wide spread of numbers between the 7 and the 65, I just put the 7 and the 65 on my graph. So 7, open circle, doesn't include 7-year-olds, and then shade to the left. T is greater than or equal to 65, color in that circle, and then I want to shade to the right. Alright, let's take a look at some others. Here we're going to go the other way around. We are going to write a compound inequality that could represent this situation. In the first example, you notice it's between these two that are shaded, and it's highlighted that it is shaded in, so I do want to do -10 and 5, and it's between them, so my less than or equal to, and then put my variable in the middle. In the second example on the bottom here, shaded in, but then it's shaded to the left, so I have x is less than or equal to 3, or I have x not shaded in, so greater than 10. Here are a couple of compound inequalities that I want to solve. Now these are AND situations. Even though you don't see the word AND in them, these are AND problems. Compound inequality is going to have more than one inequality in the problem. And when I solve this, well, it has parentheses, so I want to make sure that I distribute to get rid of them. So -5 is less than -4x minus 32, which is less than or equal to 16. And now my goal here is to get the x by itself. It's in the middle. So I use the same steps I use in solving equations. I have to undo the subtraction first, so I'm going to add 32. But there are 3 sides to this inequality. There's the left side, the middle, and this right side. So I need to do it to all 3 sides. So -5 plus 32 is 27, is less than -4x, which is less than or equal to 48. Now I want to divide by -4, and then when I divide by -4, these are going to cancel in the middle, but bells and whistles should be going off because I'm dividing by a negative. What do we do when we divide by a negative? We flip the inequalities. 48 divided by -4 is a -12. And over here, 27 divided by -4 would be a -6.75 or -6 3/4. Now, this is really saying that -6.75 is greater than x, which is greater than or equal to -12. The smaller number is this -12. So I want that -12 written on the left-hand side and the -6.75 on the right-hand side. And see how it's pointing to the -12? Keep it pointing to -12, pointing to the x, keep it pointing to the x. This is my solution. I want to make sure that I always have the smallest number on the left-hand side. So when I go to graph this, let me put some dashes on my number line. Let's make this -12, that would be -10, -8, -6. So when I go to graph this, I want to close circle at negative 12. I want to open circle at negative 6.75, so around in here somewhere. And then I shade in the middle because x is sitting in between the two. Taking a look at problem number 8 down here, I have another compound inequality because I have the two inequalities. So to solve this, my goal is going to be to get that x by itself. Now in the middle here, this counts as one big fraction. So I have to undo that divided by 4. That means I have to multiply each piece by 4. So 4 times 0.5, 4 times a half is 2, less than, well that 4 is going to cancel with that 4, leaving me with 3x minus 1 is less than 5 times 4 is 20. Then I'm going to add 1 to both sides. So I have 3 is less than 3x, which is less than 21. Divide all the sides by 3, and I get 1 is less than x, which is less than or equal to 7. So when I come over here and graph it, so 0, 1, 2, 3, 4, 5, 6, 7, 8. That means an open circle on the 1, closed circle on the 7, and since x is sitting in between them, I am going to shade in the middle here. Shade in the middle. I'm trying to get that shaded with my pen. Now these next two examples are also compound inequalities. These are just not the and type of situations. If you notice in the middle, they have the ors in there. So these are the compound inequalities with or. The way we solve them is we start off with the inequality on the left-hand side, and we start going through and solving this like a regular inequality. I want to distribute first, and then I notice I have some like terms I want to put together. So 3x minus 2s is x, so x plus 3 is greater than negative 16. Then I need to subtract my 3, and I get x is greater than negative 19. And I'm going to bring my or down. On the next one, once I get done solving the one on the left, then I go to the one on the right, and I start solving that. So I'm going to add 4 to both sides. And I get negative 2x is greater than 9. Divide both sides by negative 2, I get x is greater than negative 4.5. Now when I go and solve this, or put this on the graph, I graph both of those inequalities, and whatever they do, they do. They do not have to overlap. More than likely they're going to go in opposite directions, but they don't have to. So if I do my number line, well, I got to get a negative 19 in here. So I'm going to say that's negative 19, a bunch of dashes, and I got to get to a negative 4.5. And x is greater than negative 19 would look like that I have to do an open circle on negative 19 and shade to the right. This x is greater than negative 4.5 would mean an open circle there and shade to the right. So really what's happening is I still have this open circle, and then everything to the right would be shaded. Now normally an OR graph looks like arrows going in opposite directions, but they can overlap like this one, and if they do, this x is greater than 19 overrides the other x is greater than negative 4.5. Let's take a look at the next example. To solve that, what I would do is take the one on the left, I would add my 8, so then I have 3.2x is greater than 16. I want to divide by my 3.2, and I get x is greater than, x is greater than 5. I'm going to bring the or down, and 2.3x plus, because I have to distribute this, 2.3 times 4 is 12, carry 1, 8, so 9.2 is less than 15. Subtract my 9.2, and I have 2.3x is less than, and 15 minus 9.2, I got 0.8. I got 5.8, so divide both sides by my 2.3, and I have x is less than, so I divide 5.8 by 2.3, and I get approximately 2.52. So when I go to graph this solution, x is greater than 5, open circle, and on shade to the right. X is less than 2.52, so it's roughly in here. And then I shade to the left. Okay, and there you go. There's compound inequalities.